Hi, y'all. So you know what happens when you put earbuds in the wrong ears? They don't fit. Just found that out. Glad socks don't work that way. All right. Anyway, back to what you guys are here for. We are going to take a look at mass spectrometers. And in order to do that, let's see here, get things going. So we're going to take a look at mass spectrometers in this lecture. A mass spectrometer is a device that will allow us to basically get some clues about what a particle is. All right, so we're starting out with the force on a charged particle in a magnetic field is, well, QVB sine theta. All right, great. So what happens if we've got a charged particle moving through some region of space and we turn a magnetic field on? Well, we already know it's going to start to curve. And specifically, what happens if we've got the velocity and the magnetic field perpendicular to each other, then this thing will curve around in a circle. If the velocity and the magnetic field were parallel, then this thing, the charged particle wouldn't curve at all. It would continue to go in a straight line. Or if they were anti-parallel, there we go. This charged particle would just continue to go in a straight line. But in the case of maybe theta's equal to 90 degrees, let's see, I need to turn on there we go. In the case of maybe theta is equal to 90 degrees, what's going to happen? This thing is going to curve around in a circle. If theta were something other than 90 degrees, and other than 0, this charged particle would move in a helix, kind of like the threads on a screw. All right, so we've got theta equal to 90 degrees. Charged particles moving along happily. Let's see, magnetic field is turned on. The result of this is a force that's going to cause this charged particle to move in a circle. Move in a circle at constant speed. That's uniform circular motion. And we know if we've got uniform circular motion that there's got to be some force that's causing that. And that force, let's see, if we got uniform circular motion, then our net force, well, net force is always equal to ma. But if this thing is moving around in a circle at constant speed, then this acceleration is going to be equal to v squared over r. That's centripetal acceleration. So we'll plug that in for acceleration, and what do we get? We get this expression right there. We know the force is equal to QVB. If I've got theta equal to 90 degrees, the sine of 90 degrees is 1. So that sine of theta just kind of disappears. I end up with QVB is equal to mv squared over r, and I can rearrange this thing. And when I do, well, I can solve for what the radius of curvature would be. So r is equal to mv over qb. So if I know the mass of my particle, the velocity of the particle, the charge, the magnetic field, seems like I have to know an awful lot, that I can figure out the radius of the circle that this charged particle will move in if my velocity and my magnetic field are perpendicular, 90-degree angle. By the way, you guys can't hear it, but I've got cats tearing through here, chasing each other. So that's an awesome distraction right now. Cats, kids, everything. And apparently now I'm drawing on the screen too. Make it stop. Oh, I didn't X out. Okay. This is the second take of this video. There won't be a third, hopefully. So what do we have here? Well, up at the top left, it says mass spectrometer. So this is one form of a mass spectrometer. There's like 4 different forms of these. This is one. This is the simplest one that I know of, but I don't pretend to know everything about these. So what happens here? We've got a source of charged particles. We've got ion source there. And charged particles are emitted from our opening in our ion source right there. So positively charged particle, it's supposed to be a positive sign. And when they're emitted, they've got no velocity. But if we look, we've got a potential difference here right there that's causing a basically negative potential on that metal plate up at the top and basically a positive potential down here. So our charged particle is exposed to some potential difference. And we know that when we've got a charged particle exposed to a potential difference, it's going to accelerate. And we can use our conservation of energy equation, our E initial is equal to E final, to figure out if the starting velocity is 0, what the velocity is right there when it enters into, when it passes through a hole in that metal plate, when it enters into the magnetic field. So we're going to have some energy Q delta V that's going to be transformed into kinetic energy, 1/2 mv squared. The small v there, 1/2 mv squared, that of course is velocity. The capital V is potential, voltage. So that's great. So we've got an expression for our final velocity, or our velocity when this charged particle enters the magnetic field. If we know the voltage, the delta V, that's being supplied or being put across this region in space right here. All right. What happens when it enters the magnetic field? Well, we figured that out. We said that R is equal to mv over qb. So once it enters the magnetic field, it's going to have a radius of curvature that's based on its mass, its velocity, that's a small v there, its charge, and the strength of the magnetic field. If we check out, we think about our right-hand rule, we think about, let's see, this charged particle is entering this magnetic field. Which way does the magnetic field point? The magnetic field points out of the screen. So if I'm sitting here watching this, the palm of my hand should be facing my face as a watcher, as a viewer. The back of my hand should be towards the screen. And now let's see, the velocity is upwards. My fingers curl in the direction of the magnetic field, which points out of the screen. If I'm a viewer, I know everything's flipped because of the camera, and don't let it confuse you. And my thumb points towards the right. And that makes sense because, well, we can see the pathway the charged particle takes. It looks like it's curving to the right. Okay, so what I'm going to do is I'm going to rearrange this R is equal to mv over qb equation a little bit. Let's just make it so that qrb is equal to mb. Why did I do that? Because I would like to take these two expressions right there and kind of meld them together, because there's no easy way to know the velocity of this charged particle. But if I know the voltage I'm supplying, then maybe I can figure that out, and maybe I can meld these two expressions together to figure out exactly what's going on. Got kids screaming in the background. Cats, I don't know. This is insane. So anyway, I'm trying to figure out, trying to eliminate velocity out of these two expressions by combining them together. So I'm going to rearrange this one. QRB over M is equal to B. All right. And now I can take that and I can plug it in right there. All right, plug it in for V. So let me do that. So it looks like Q delta V is equal to 1/2 M times, well, the bottom expression there, squared. All right. Let's buy ourselves a little more space and move on to the next slide here. Sounds like the cats jumped up onto our bookshelves and knocked over a picture and broke glass in the picture frame. So let's see here. That's fun, but like I said, this is the last take of this video. So let's see. I've got last expression I have said that 1/2 m times, that's supposed to be parenthesis, times QRB over m squared is equal to Q delta V. Okay. All right. So let's carry out that square. And I've got my, let's carry out that square. I end up Q squared R squared B squared over M squared is equal to Q delta V. And I can simplify this a little bit. I've got an M there. I've got a square there, so I can get rid of the M and the square. I've got a Q squared on the left-hand side. I've got a Q on the right-hand side, so I can get rid of a Q there. And then let's rewrite this. I've got 1/2 Q R squared B squared over M is equal to delta V. Okay, well, I can do a couple things with this expression. I might be interested in knowing what the radius is that this charged particle takes, or I might be interested in the what's called the charge to mass ratio. Charge to mass ratio, what is that? That's Q divided by M. If I know that charge to mass ratio of a particle, a lot of times I can identify what the particle is. So let's take this expression right here, put a little star by it, and we're going to rearrange it in a couple different ways. If I solve for R, I get out the expression that R is equal to the root of 2m delta V over QB squared. All right, so that's one. And then, so let's see, that's great. So that would tell me if I knew what this charged particle is, and I knew its charge, if I knew its mass, I knew the charge Q, if I knew the potential difference that it was accelerated across, and I knew the magnetic field, I could figure out exactly where it would hit on the wall of the mass spec. I could figure out the radius of its pathway. So that's one important result out of the start equation. What's another one? Well, let's write down what the charge to mass ratio is. Charge to mass ratio is going to be 2 times delta V over R squared B squared. All right, so that will give us our charge to mass ratio if we know exactly where the particle hits, which that's what we would do with a mass spec. We would turn it on. We would control the magnetic field and the potential difference. Use a detector to figure out where the charged particle hits the wall. Let me go back a slide. Let's see here. Okay. Figure out where that charged particle hits the wall, basically right there. Yeah, that would give us the R, the radius of the pathway, and then based on that information, we could solve for Q divided by M, and then consult maybe a bunch of tables to figure out what our particle likely is. A bunch of tables of charge to mass ratios. All right, so let's do an example problem here with this. And let's need to clear all this mess. Oh, So this is a little bit of what we just talked through. There's one more result, which we could solve for the mass if we wanted to, using that asterisk equation to get this expression. But okay, that's fine. That's all well and good. Let's look at an example problem. All right, so in this one, we've got neon in a mass spec. Neon has got an atomic mass of 20.2 U. That's 20.2 atomic mass units. So we've got the mass. We've got the potential difference that this neon is accelerated through. We've got the size of the magnetic field. And one other thing that we have here that's a little bit hidden is we've got the actual charge of the particle. It says that this thing is doubly ionized. Well, what does that mean? It means that we have 2 electrons stripped off. So we've got 2 missing electrons. So our charge is going to be twice the fundamental charge, which is 1.6 times 10 to the negative 19 coulombs. Our charge is 3.2 times 10 to the negative 19 coulombs. All right, what are we actually asked for? We're asked to solve for the radius of the pathway that this thing takes. We've got Q, we've got magnetic field B, we've got our potential difference, delta V, and we've got the mass of this thing, 20.2 U. Well, that's great, but we don't usually work in atomic mass units. We work in kilograms. There is 1.67 times 10 to the negative 27 kilograms per atomic mass units. So when we do the math there, we end up finding that our mass is 3.37 times 10 to the negative 26 kilograms. All right, awesome. Oops. So let's see, what is it we're solving for? We're trying to find the radius. And you know, we can use that expression that I had a slide or two ago. It says that radius is equal to the root of 2m delta V over QB squared. Yeah, okay. And we can fill in our numbers. Twice 3.37 times 10 to the negative 26th times our delta V of 500 volts over the Q of 3.2 times 10 to the negative 19 coulombs times 2 Tesla. And we're squaring that. And when we do all this, we get out that our radius is 0.00513 meters. Or what would that be? That'd be 5.13 millimeters if we were interested in that. If we wanted to know the diameter, what would we do? Well, we'd just double that number, but that is our result right there. Okay. And thank you guys for watching. I have to go clean up a broken picture frame. Bye. No, really, bye. Good. Bye. Bye.